goed. Ja.
Ja, maar ik heb het ook wel eens gehad en ik zo, zeg maar, no time, vraagteken en dan was het zo,
Okay, welcome to today the last lecture on the multibody dynamics. If I look at the number, we have 11 lectures, 10 homework assignments, and the Edu board talked with me about study lost. How do you say? Yeah, and I understand this year with the peer review grading, it's all a little bit hard and more time, and people are complaining and it's so much, and so I dropped a topic in the unfortunately, but anyway, it is still in the book. I dropped a topic on other ways to describe orientation. So the thing with axis angle, it's in the book. Euler parameters, it's in the book, but it's not part of the curriculum this year. Just to relax a little bit on the topic and the content, and to make the ACTS comply with your work. And of course, I dropped a number of lectures. Right, this is the last lecture. We have no more lectures. The next time we see each other is at the exam. And if I do it by head, and that's very dangerous, it's on a Friday in July, the first week. And if I remember well, the number is 5, July 5. A digital exam. I will put an example of the digital exam. It's in the Maple TA environment. I think there is already an example. If it's not there tonight, I will put it. there, and then you can practice with that example, just to see the look and feel, how does it work, and because in the digital exam, it's a bit different than from the weekly tests, where you only could give one answer. Now you have more chances to give the correct answer, and if you have a wrong answer, it tells you, well, it's wrong, but maybe you made a sign error, and try again. And if it's wrong the second time, they say, well, did you really understand the problem? Because maybe you have to do this, this, and that, so you get some content help. And then again, you have 2 chances to give the correct answer. So in total, you have 4 chances per assignment. There are 3 assignments in the exam. And of course, the maximum grade goes down. It starts with 10, and then 9, and then 6, and then 5, and then it's gone. But I'm not going to talk about it much. Just practice. Yeah, question.
Will we have MATLAB?
Will we have MATLAB is the question. Yes. So it's an open book exam, in the sense that book is also a digital book. So please take all your stuff, your homework with you, your homework assignments, your worked out assignments on disk, on stick or whatever. On the computer, there will be running MapleTA, but you will be able to run MATLAB, view PDF files and Word documents. You will not be able to access the internet, for obvious reasons, and there will be no way to communicate with others. It's an individual exam. But you can calculate whatever you want. You cannot use your own electronic devices like smartphone or laptop. USB stick is okay, as long as it has no Bluetooth, Wi-Fi, whatever thing in it. Whatever, I don't think they have. Yeah. Any other questions so far on that exam? Nah, it should work, right? Okay. So we start today with the last Kahoot already, right? Now, I have a special request for those who are in the WhatsApp and do not look at the questions. I have no problem with that. If you want to do that shortcut, that's okay by me. However, in this quiz, which is 12 questions, the first 5 are about content, and the last 7 is about your experience in the course. And if you just randomly press one of the buttons for the last 7 questions, it sort of disrupts my whole enquete on your experience. So those in the WhatsApp, please only answer the first 5 questions. The rest even doesn't count for your grading, so forget about it. The first 5 is okay. So if somebody can say that in the WhatsApp group, only the first 5 count, forget about the containing one, the rest, then I'm super happy. Okay, Kahoot, where are thou? Kahoot. Yeah, thanks, maybe later. My Kahoots. Number 11, well, play, right? We are very classic. Okay, let's start. So, yeah, 12, so 5 content questions for grades and 7 just to know what it's all about. Get feedback from you. this shouldn't be so hard, right? Oh. I'm a bit disappointed by 27. Well, this is a bit strange, but 27. Well, anyway. It's 6, of course. It's a symmetric thing, RT, R transpose. So instead of 9, you only have 6, the diagonal and the off-diagonal terms. Okay. A number of independent parameters. Now we go into a 4-dimensional space. I have no clue what it is, but I know the math in this 4-dimensional space. Please discuss with your neighbor. Convince him. Yeah. Again, majority is right. I think there's an explanation in the book for those who are wrong. I want to continue because we have a lot of questions today. This is about the rotation matrix. Look very closely at the indices, the B, N, and where are they, and what am I asking? Yeah, discuss, huh? Okay, so this asks for some feedback. Yeah. So what am I asking? So here we have from an inertial frame to a body fixed frame, we have just a sequence A, B, C, 3 rotations. And but I'm asking the transformation. I'm asking is not given the body fixed, what is the frame fixed, but the other way around. Given what the a vector is in the inertial frame, in this frame, what is it in this body fixed frame, B? So you have to walk backwards along this thing, yeah, along this chain. Now, there are various ways to solve it. First you say, well, I know what the forward chain is. That's RA times RB times RC. And backwards is the transpose, and in the transpose all the order changes. So then finally I get RC transpose, RB transpose, RA transpose. That's a simple answer. You could also think in a more sophisticated way, well, like I know that the inverse is the transpose, or that's with the minus A, that's identical. And then if you have to walk the chain backwards, then, oh yeah, looking at the picture again, I have to walk from here to here, then I have to walk this thing, but then backwards, right? So transpose this thing and this thing. So a second reasoning for the correct answer. For those who are wrong, read again in the book this part on the inverse and transpose. Okay. Angular velocity matrix is a beautiful matrix. Very quiet in the room. Discuss, convince. Use your voice. Yeah. So, instead of giving the correct answer, I learned from doing multiple choice that you also have to do this trick. It's sort of a trick, right? If you look it up, the answer is that it's asymmetric matrix, right? So symmetric cannot be true. Non-singular. This asymmetric matrix is always singular. There's always all zeros on the diagonal. And Hermitian, I have no clue actually what it is. You just look up on Google the type of matrices. You get Hermitian. I don't know, something with imaginary numbers. Complex conjugated is transpose or something like that. I don't know. Anyway, so it's none of the above, right? That was super clear. Okay, this is a hardcore calculation. That's what you can do. Easy, right? You have 90 seconds. Very simple problem. You can also use your intuition and then give immediately the correct answer or just calculate. Yes, very good. So there are various strategies to find the correct answer. You can look at last year's quiz. I think it was there too. Let's look at the problem again. So apparently we have a rotational speed around the x-axis and the z-axis and not about the y-axis. An example could be, for instance, a bicycle wheel. It's rotating about this axis and then the bike is falling over. So that's, let's call this the z-axis, let's call this the x-axis forward. And then and we have some mass moments of inertia. And then we know that the bike will steer into that fall automatically. So we get a torque about the third axis. Well, if you don't know, you just calculate, right? You just do I omega, omega cross that, and then minus I. But then the physical thing is that apparently, I have to go back to the media. Apparently, when the rotation is about this x and z axis, you get a torque about this y axis. That's the gyroscopic effect. It's always this three-dimensional thing. Rotation this, you get a torque like that. You can feel it with a wheel and tilting. So this is the correct answer. This can't be right, and these, well, I don't know. Okay. Yeah. So WhatsApp group, say bye-bye. The next question, if you do not look at the questions, give a sincere answer. That's what I should say. Honest and sincere answer, then just don't answer, because the grading is not going to work for the rest of these questions. Okay, what are the questions? Time spent on average per homework assignment was, for me, and just be honest. These, I will anonymize these answers. I will never connect these answers with your identity. I solemnly pledge. Okay, that's good to see. Yeah. Informative, right? Yeah, everybody seeing it? Okay. This is about the live stream and the lecture. So about what did you attend? Was it live stream or lecture room, or you didn't attend? Oh, or recorded lectures, of course. Yeah. Yeah. This is really the example of a select test, right? Because who is watching this? Okay, well, I'm not going into this. Interesting. In doing the homeworks, the TAs were, I love the TAs, I hated them. They were okay. Oh, that's a good feedback. Not so helpful. Yeah, I'm interested in details. So if somebody wants to exemplify on this, please contact me. Yeah, and again, it will be anonymous. I will never connect you to. Okay. If there was no live stream, then I would be. Okay. Oh. Okay. The recorded lectures were, if they were used and useful. So it's a combination thing. Yeah, the things I learned in the course. Well, you don't have to mention them all, but say what level was it? More than you expected, what you expected, less, or actually I learned very little. Okay. Yeah, the last question is maybe the most important one. Would you like to be a TA for this course? And it complies very well with the scoring on the helpfulness. So yes, maybe, no, never. Wow, 22 nevers. That's good to see. Yeah. Okay, thank you. Yeah, that was sort of fun, right? Now I have to save everything. Okay, feedback. Hey, aha. That's funny. So the feedback on this was a lot more positive than last week, last time. Maybe it has to do also with the live stream not being up or whatever. Okay, thank you. What are we gonna do? The thing is still live, so I'm happy. We go to this. Yeah, content, right? Okay, and this is all running. Yeah, that's also good. Okay, let me get organized here. So what am I going to talk about today? So again, rotation matrix, Euler angles, and equations of motion. So how do you then use this knowledge to formulate your equation of motion? That is actually the topic of today. And since last week, the last lecture was a bit chaotic at the end and I had to speed up. The part on the angular velocity, I still want to discuss some things about that. So I want to do, again, a quick intro to angular velocities. So remember, so now I want to talk again about angular velocities and a little bit, velocities, and a little bit more in detail. Remember that we had that we said the position of a point is the position of the center of mass plus the relative position of that point with respect to the center of mass. That's how we start. We have some potato here with some coordinate system, and there's some point P in here, and then this is this vector, this x P relative to C. I still haven't said in what coordinate system this is. We have some reference coordinate system, some inertial system, which we usually donate by n, and then we have some body fixed frame. You can pick any letter, but for now B seems appropriate. Usually we identify this with x, y, and z, and here we usually write x prime, y prime, and z prime. I hear conversation in the back. That's disturbing for me. It interferes with my talking. So either go out the room and continue your conversation there, or shut up. Okay, so this is kinematics, what the finding the position. And then the velocity is actually super simple. X dot p, so the velocity of this point is the velocity of the center of mass plus this relative velocity. Nothing new there. Now the thing is, how do we find this position of P with respect to C? And for that we use rotation matrices, right? We said, oh yeah, there's a nice thing, P relative to C, I find with the rotation matrix because then I have this vector which is in the body fixed frame, and that is constant. And then the only thing which changes is the rotation orientation of the thing. Okay, so if we then use that thing, and then we write out x dot p relative to c is then r dot x prime p of c plus r x dot prime p of c. And of course this is 0 because it's a constant. That was super. And then we focused on this one, and I said, well, the disadvantage of, it's nice that this is a constant, but the disadvantage of this thing is that we work in two different coordinate systems. And I want to work in one coordinate system. So therefore I put again this relation into this equation. So what I get was x dot p of c is r dot. Now I need the inverse of the transformation, because I need to go from prime to this one. Remember the homework question. So I get the transpose times. So now both vectors are in the same coordinate system. And then we focus on what is this matrix. So what do we know about r dot r transpose? If that is a rotation, apparently that stands for rotational speed. Rotational speed. But how does it stand for that? Well, we have the identities, of course. We have r times r transpose was these identities. And then if we differentiate that with respect to time, so we do d dt, then what do we get? R dot r transpose plus r dot transpose is 0, all zeros. And looking at this, I said, well, that looks like that this guy is sort of the transpose of that guy. So if we then, for instance, define W, some matrix as r dot r transpose, then we can write this as W plus W transpose is 0. And if W is a matrix, and it's a 3 by 3 matrix, then I know that W must have this structure. It has all zeros on the diagonal. Because if you transpose the thing, then the diagonals stay the same, and the result must be 0. So there must be zeros on the diagonal. And what is here on the plus should be here minus on this side. But then again, I have a strange way of writing that. Instead of saying A, B, C, and here minus A, minus B, minus C, I'm going to write it in a peculiar way. I'm going to write A here, the B here, and the C here. Very strange way. And meaning then we get here minus A, minus B, and minus C. Now why do I do that? So it's skew or asymmetric. I don't know what exactly the difference is. I think it's the same, but or I should say or asymmetric. So why do I write it like this? Well, if you now take some vector, you do W times a vector X, then how does that look? Well, here we have X, Y, Z, and here we have this strange A, B, C with here the minus A, minus B, minus C. And if I write that out, then I get on the first line, I get minus C times Y plus B times Z. And I get C times X minus A times Z. And I get minus B times X plus A times Y. Looking at this looks a lot like a cross product. With this, on the first line there's no X, on the second there's no Y, and there's no Z here. Or in other words, this W times X looks like I have a vector W cross product with X, where the vector W is just A, B, C cross X, Y, Z. So that's 3 elements. And of course this thing only has 3 elements, this asymmetric matrix. And then finally we make the step and we say, oh, there is a way to write this matrix W. We can say, well, if we write W with a tilde, then that is the matrix, and is this matrix, which complies with this W vector. Anyway, if we then go back to finally our beginning, X dot is R dot R transpose times X, then we say, oh, that's apparently this W matrix times X, or in other words, that's this W vector, cross product with X. And now, I should make vectors out of this, sorry. Now finally comes the definition. Then we say, by definition, we write this as omega cross X, and we say omega is the angular velocity about X, Y, and Z. And that is the definition. This is actually the definition of our angular speed. So in a natural way, we now have come up with angular velocity in a three-dimensional space and how it is connected to our rotation matrix. Okay. Now remember that we parameterize R by Euler angles, right? So you could write R is some R of, and we started with phi theta psi, I think. What do we usually do? Yeah, there's a whole set of Euler angles. Yeah. Okay, phi theta psi. Three angles. So with these three angles, you only have these three parameters, right? Now, now we can relate what these time derivatives are to our angular speeds, because we have the matrix here, which is a function of the three angles. Then we have to formulate this one. We have to just write down R dot R transpose, and then equate that to this omega tilde matrix, which is, let me write it out again, 0, 0, 0. Here we have omega x, here we have omega y, and here we have omega z, and here we have the minus 1, minus omega z. So expanding this one, well, it is not a function of time, but a function of the parameters. But the parameters are a function of time, so then you have to do first a partial differentiate to the parameters, and then the parameters to time. So first R with respect to this angle phi times R transpose times phi dot, plus, and we have three angles, so we have to do that for all the three angles, theta R transpose theta dot plus dr d psi R transpose psi dot equals, and then we have this omega matrix. Now let's pause here for a moment. Omega y, z, sorry, minus omega y, minus omega z. Okay, let's pause here for a moment. So the right-hand side is clear, right? Zeros on the diagonal, and here numbers and here numbers, which actually are the anti of each other. Then on the left-hand side, that's also clear. That's just doing algebra, just taking partial derivatives and multiplying. But interestingly, if you look at these equations, we found three ways to calculate zero. Or in other words, you have a way to, if you do it all correctly, you have a way to check your work. Apparently, if you go through the motion here, you will get a 0 here, a 0 here, and a 0 here. And that looks a bit magic, because this matrix is a triple product of sine and cosine of the three angles. Very interwoven, all these three. And then what do? You differentiate it to one angle. Well, the sines and cosines remain. They do not disappear. And then you multiply with the transpose, so you get up to products of 6 sine cosine things multiplied maximum. And then apparently on the diagonal, lo and behold, I get all zeros. And on the off diagonals, I can calculate omega x, but for free, if I do all the six entries, for free I get minus omega x. So there are a zillion ways to check your work. But on the other hand, you would expect this to be very complex. Now, what are we seeking? We are seeking the relation between omega on the one hand side and the time derivatives of our angles on the other side. That's what we're seeking. Because our Euler equation, the Euler equation is written like this. Euler equation of motion is sum of the torques is a mass moment of inertia times omega plus omega cross I omega. So everything is in omegas. Everything is in omegas. But we do our parameterization in 3 angles. And the 3 angles, the time derivatives are not directly these omegas. Apparently there's some complex relation. So we have to find that complex relation, because these are state variables, but here we have another equation for the change of our speeds. Okay, so how do we go about? Well, you can expand this, that is one way, but there is a more intuitive way. I always say, although intuitive ways are super dangerous, and the intuitive way is to again use that picture to say, well, let's draw these cans in series. So the first one, axis, z, this is z, this was x, this was y. The first rotation is this phi about the z-axis. So I take the standard Euler angles. Then the second one is about the x-axis. And then the last one is about this one, again about the z-axis. And then finally here at the end we have this body fixed frame, right? X prime, y prime and z prime. We could put this n here and we could put this b here. And this was the theta, right? And this was the psi. Okay. Now looking at the picture and you have these direction of these cans, you can say, well, the angular velocity omega vector, which is some vector, I just draw something, so omega vector, something like this for the body, the current omega. That omega vector is actually the sum of these 3 rotational speeds around these axes, right? So I can say, oh, I have a vector here, which I will call omega theta. I have a vector along in this direction, which I will call omega theta. And I have here a rotational speed vector, and that is omega, let's move the paper a little bit, omega psi, right? So 3 rotational vectors. And the total vector is just the sum of this one. It's the first rotational speed plus the second rotational speed plus the last rotational speed. Now note, I haven't said in what coordinate system I'm expressing this. Because the problem here, and that is the problem with rotation always, this rotation speed is in the inertial frame, that is clear. So if we want to know what is the angular speed, for instance, in the inertial frame, then this one is clear. That's always the z-axis. That won't change, right? So we can immediately write, oh, that's 0, 0, what is it? Phi dot. Plus. But this axis, that will change, right? That will change due to this rotation. So this axis changes due to this one rotation. It has nothing to do with this one, but due to this rotation, it will change in this coordinate system. So we can say, well, it is initially maybe about the x-axis. So we can say, oh yeah, it is about x-axis, θ dot 0. But when the things rotate, then we have to take into the counter rotation of this thing. So we have to bring this vector into this frame. Well, we are very apt with that already. So we have to multiply with r phi. And then finally, the last one, this about the psi axis. Again, we know it's about the z-axis. Yeah. So finally, we say 0, 0, psi dot. But then there are 2 rotations in play here. So first, from this system, we go back to this system. So we have to rotate with this. The last rotation doesn't matter, right? Because it's the axis of rotation. So you can rotate whatever you want. Any vector along the axis of rotation doesn't change. So we don't have to take, you can take it into account, but nothing happens. Because 0, 0, 1, 0, 0. So we can forget about this one. This rotation we have to take into account to bring it into this coordinate system. And then this rotation we have to take into account to come into this rotation system. So first we have to do the r theta, and then we have to do the r phi. From this body to this one, and then we're there. Now, looking at this one, this looks a lot easier than this expression, right? This looks very complex. This is sort of doable to expand. Now, let's try and do that. So, I found the following result. Omega z equals. At most, we will get a double product of sine and cosine. Have two different angles. It can't be higher. And there's only this. Now I have to write these in a certain order, and notice what I do. So I write phi dot, because that's the first one, theta dot, and then psi dot. Note this is not a vector. So this is not a vector. Although I write them as an ordered pair, it's maybe an ordered pair, but it's not a vector. It's just an ordering. And it becomes even more clear when you look at this expression, because the phi dot here is the third, and the theta dot is the first, and the psi dot is the last. That maybe also helps you to say, oh yeah, there, you cannot look upon these as vectors. Anyway, I order them like this, the time derivative of the order, because it's three numbers and I have three numbers here, so it makes sort of sense. And now, what is the outcome? Well, yeah, let me copy this. So 0, I get cosine phi, I get sine phi, sine theta, I get a 0, I get a sine phi, I get a minus cosine phi, sine theta, yeah. I get a 1, a 0, and I get a cosine theta. As we expected, right? Only at the most a double product coming from this one. You see that the last two rotations have no effect on the z1. Well, anyway, there are a number of zeros here which you can explain that this one, this phi dot, has no effect on the omega x, and the theta dot neither. And of course this one is directly with 1 put on the z, but of course with the psi dot on the last one we also have a contribution. But it depends on the orientation of the middle axis. It's the sum of these two. Anyway, it's interesting, this relation, but what we need is the other way around. The state, we define our state. We define our state, in this case, as we have the angles, and we have omega x, omega y, omega z. Why? Well, because for this we have state equations, right? The state equation for this one is Euler. We have omega dot equals I minus 1 times the sum of the torques minus plus minus omega cross I omega. We have a nice equation for this. Now we need a state equation for this. So we need to know the time derivative of the Euler angles as a function of our state. Well, here we have them, but we have them the other way around. So we have to know these as a function of this and this. So we do the inverse, right? So we get phi dot, theta dot, psi dot equals, and then what we get is here omega x, omega y, omega z. And then what are the entries? I don't know by head. Oh. I need the book. Does somebody have the book? I forgot to take the book with me. Yeah, it's in the book, therefore, sorry. Yeah, thank you. Okay. So then we go to, yeah, here it is. Is it in the book? No, I didn't write it in the book, right? I only did the relative ones, yeah. Anyway, we have to do the inverse. Well, that's not so hard. We can do that. Then we have to form the determinant of this one. Yeah. So let's call this, how did I call the matrix? Usually I call this the B matrix, or did I call it A? I don't remember. A? B. I called this B. So this is a B matrix, and this is what I call then an A matrix in the end. So how do we find this A matrix? Well, we have to take the determinant of B, right? And then we have to take subdeterminants. Now, since there are a lot of zeros, it's super easy to find the determinant of this matrix. This is already 0, so then I get cosine phi with a minus cosine phi sine theta. So that's this one to this one, and then this one to this one, that's all zeros, and then minus, and then I get this one, that's a sine phi sine theta. Oh, so I get, this is cosine squared, this is sine squared, so I get minus cosine phi squared plus sine phi squared times sine theta. So the determinant is super easy, that's minus sine theta, right? So I have to write here 1 over minus sine theta, and then I have to form the entries. But if this is the determinant, then when can the determinant for B be 0? Yeah, when theta is 0 plus or minus k pi, right? And that is a problem. So already in the initial configuration, so in the configuration which we drew here, we cannot find the inverse relation. I mean, we given what these speeds are and what the orientation is, we can calculate what the omegas are, but the other way around is apparently not possible in this configuration. Problems. To solve problems, we need coffee. Coffee break.